Scientists have studied black holes for decades, yet every discovery raises more questions than it answers. What happens at the center of a black hole? Could they connect to other parts of the universe, or even other universes? Are they destructive monsters or cosmic engines of creation? From ideas about time travel to theories that black holes could power advanced civilizations, the possibilities seem endless. Let's dive deep into the most mind-blowing mysteries of black holes, exploring not just what we know, but what we might know if we dare to imagine. Prepare for a journey into the unknown. Does the no-hair theorem hide more than it reveals? The no-hair theorem asserts that black holes, despite their immense complexity, can be fully described using just three basic properties: mass, charge, and spin. These parameters are the only external signs of a black hole's presence, meaning all other details about the matter that fell into it, its composition, structure, or history, are effectively erased. The name no-hair reflects this simplicity, as if the black hole's appearance is stripped of any distinguishing features beyond these three. On the surface, this simplicity is appealing. It provides a clear framework for understanding black holes without delving into the chaotic specifics of what goes on within. A black hole with the same mass, charge, and spin as another is indistinguishable from it, regardless of how they formed or what they consumed. But does this simplicity tell the whole story? Or does it obscure deeper truths about these enigmatic objects? Black holes exist in a universe brimming with complexity. They form from the collapse of massive stars, which are anything but simple. Stars have layers, varying chemical compositions, and histories that span millions or even billions of years. When a star collapses into a black hole, where does all that complexity go? The theorem tells us it vanishes, leaving only mass, charge, and spin. But the mechanisms behind this erasure remain one of the most puzzling aspects of black hole physics. According to quantum mechanics, information about a physical system can never be completely destroyed. Yet the no-hair theorem implies that all details about the matter falling into a black hole are lost forever. If a black hole eventually evaporates through Hawking radiation, as theoretical physics suggests, where does the information go? This contradiction between the no-hair theorem and quantum mechanics has been a subject of intense debate for decades. Some researchers argue that the no-hair theorem is an oversimplification. They suggest that black holes might possess subtle features, often called quantum hair, that preserve at least some information about the material that formed them. These features would be incredibly faint, almost impossible to detect with current technology, but their existence could resolve the information paradox. If black holes have these hidden traits, it would mean the no-hair theorem, while useful, doesn't capture the full picture. The no-hair theorem applies to isolated black holes in a vacuum, but such conditions are rare in the universe. Most black holes exist in dynamic environments, surrounded by gas, dust, and other objects. These surroundings can create complex interactions, like accretion disks, or powerful jets of radiation. Could these interactions leave subtle imprints on the black hole itself? If so, the no-hair theorem might not account for these complexities. When two black holes collide, they form a new black hole that settles into a stable state. According to the no-hair theorem, the final black hole can be described by its mass, charge, and spin, regardless of the properties of the original pair. But the process of merging is incredibly violent and chaotic, involving the release of massive amounts of energy in the form of gravitational waves. Some scientists wonder if these waves might carry away more information than previously thought, potentially encoding details about the original black holes. Einstein's general theory of relativity forms the foundation for the no-hair theorem, but it is not the only possible description of gravity. In some alternative theories, black holes might exhibit additional properties or behave differently under extreme conditions. If such theories prove correct, the no-hair theorem might be an approximation rather than a universal law. From the intricate structures of galaxies to the delicate patterns of subatomic particles, nature rarely embraces simplicity for its own sake. Why then would black holes, arguably the most extreme objects in existence, be an exception. For now, the no-hair theorem provides a way to simplify their study, allowing physicists to focus on their most fundamental properties. But the more we learn about black holes, the more we realize how much we don't know. What lies beyond the singularity? Theoretical explorations. The singularity is the point where the known laws of physics break down, a place where densities become infinite and space-time curves so sharply that even light cannot escape. At the heart of every black hole, the singularity sits hidden from view, shielded by the event horizon. Some physicists believe that the singularity represents the end of the road for our understanding of the universe. The equations of general relativity, which describe gravity and the structure of space-time, stop working at the singularity. They produce numbers that grow endlessly, which suggests that the theory itself is incomplete. This has led many to think that a new, more advanced theory is needed to explain what really happens inside a black hole. Quantum gravity, which aims to merge quantum mechanics with general relativity, could be the key to solving this puzzle, but it remains a work in progress. One idea that emerges from quantum gravity is that the singularity might not be a point of infinite density. Instead, it could be a region where the extreme conditions create new forms of matter or energy that we haven't yet discovered. These exotic states could behave in ways that seem impossible under normal circumstances. Some researchers have even suggested that space-time itself could be torn apart and reassembled in a completely different way. Others propose that the singularity might not mark an end, but a beginning. In this view, what happens inside a black hole could lead to the formation of something entirely new. One theory suggests that a black hole singularity might act as a bridge to another part of the universe, or even another universe entirely, a tunnel through space-time that connects distant points called a wormhole. While wormholes are purely theoretical, some scientists think they could naturally form in the intense conditions of a black hole's core. Perhaps the singularity could serve as a seed for a universe like our own. This idea comes from the observation that the conditions at the singularity, extreme density and energy, are somewhat similar to those thought to exist at the Big Bang, the event that started our universe. If this is true, black holes might be like cosmic factories, each one spawning a new universe that expands and evolves independently. Not all ideas about the singularity involve distant universes or entirely new laws of physics. Some researchers believe that what lies beyond the event horizon could be less dramatic. For example, there's the possibility that singularities don't exist at all in the way we imagine them. Instead, they could be replaced by a phenomenon called a quantum fuzzball. This theory, rooted in string theory, suggests that black holes are not empty regions with a singularity at their center. Instead, they might be made up of tangled strings of energy that prevent the formation of a true singularity. Another approach to understanding singularities involves holography, a principle that suggests the universe might work like a hologram. According to this idea, the three-dimensional space we experience could be a projection of information stored on a two-dimensional surface. Some physicists think this principle could apply to black holes, meaning everything happening inside the event horizon might be encoded on its surface. If true, this could provide a way to understand the singularity without needing to look inside it at all. Inside a black hole, space-time becomes so warped that it could tear apart completely. This tearing could lead to regions where time and space no longer function as we understand them. What would it mean for time to break down? Would it stop flowing altogether, or could it reverse direction? Some believe that the singularity could also hold clues about the ultimate fate of black holes themselves. If black holes eventually evaporate through Hawking radiation, what happens to the singularity? Does it simply vanish, or does it leave behind some trace, like a remnant? These remnants could be tiny but incredibly dense, carrying information about the black hole's history. The extreme warping of space-time near a black hole has led some to suggest that singularities could allow for shortcuts through time. Could the singularity act as a gateway to the past or future? If so, what rules would govern such travel? Would it be possible to influence events outside the black hole, or would the traveler be trapped within its boundaries? Perhaps the singularity could act as a mirror, reflecting certain aspects of the universe back at us. This idea comes from the fact that black holes affect their surroundings in measurable ways, from gravitational waves to the radiation emitted by their accretion disks. If these effects carry subtle clues about the singularity's nature, studying them could help us understand what's happening inside. Black hole firewalls, the paradox that could rewrite physics. At the center of black hole, firewall paradox is the event horizon, the invisible boundary surrounding a black hole. Once something crosses the event horizon, it can never escape. According to Einstein's theory of general relativity, the event horizon is unremarkable. A person falling into a black hole wouldn't notice anything special when crossing it. But quantum mechanics suggests something entirely different, a fiery, destructive barrier at the event horizon. The paradox begins with a principle in quantum mechanics called unitarity. Unitarity states that information cannot be destroyed. Even when something is burned, crushed, or transformed, the fundamental information about it remains, encoded in the particles or radiation it leaves behind. But black holes seem to violate this principle. When something falls into a black hole, all its information appears to be lost forever, hidden behind the event horizon. This is known as the black hole information paradox. Physicists trying to solve this paradox realized there might be a problem with how we think about the event horizon. According to quantum mechanics, the particles making up Hawking radiation are entangled. Entanglement means that the properties of two particles are linked, even if they are far apart. For Hawking radiation to preserve information, the particles outside the event horizon must be entangled with the ones inside. But this creates a contradiction. A principle in quantum mechanics called monogamy of entanglement states that a particle can only be entangled with one other particle at a time. If the particles outside the black hole are entangled with those inside, they cannot also be entangled with earlier Hawking radiation that escaped. This conflict led physicists to propose the firewall idea. To preserve the rules of quantum mechanics, something must destroy the entanglement at the event horizon. This destruction would release enormous amounts of energy, creating a blazing firewall that burns anything falling into the black hole. General relativity says the event horizon should be smooth and featureless. There should be no violent effects or burning walls. A person falling into a black hole would pass the event horizon without noticing, at least until they got closer to the singularity. But the firewall paradox suggests otherwise. If firewalls exist, the event horizon becomes a deadly boundary, tearing apart anything that tries to cross it. If firewalls are real, they would rewrite our understanding of black holes and space-time. But proving their existence, or disproving it, is extremely difficult. Black holes are incredibly far away and hidden by their own nature. We can't directly observe what happens at the event horizon, so scientists must rely on theoretical calculations and indirect evidence. Some researchers believe the paradox could be resolved in other ways, without the need for a burning barrier. One possibility is that the information about what falls into a black hole is encoded on the event horizon itself according to the holographic principle, meaning that the event horizon acts like a giant screen, storing information in 2 dimensions while projecting the 3-dimensional reality we observe. If this is true, the information might never truly disappear, avoiding the need for a firewall. Some versions of quantum gravity suggest that space-time near the event horizon might behave differently than we expect. Instead of a firewall, there could be a more subtle mechanism that preserves information while keeping the event horizon smooth and passable. There's also the possibility that the paradox arises from our incomplete understanding of black holes. The equations we use to describe them might not fully capture their complexity. Some physicists think that black holes could have hidden structures or layers that resolve the conflict between relativity and quantum mechanics. These structures could explain how information escapes without the need for firewalls. The paradox challenges some of the most fundamental assumptions in physics, forcing scientists to question principles they once thought were unshakable. If the event horizon isn't smooth, it could mean that space-time itself is more dynamic and complex than we realize. This could have implications not just for black holes, but for our understanding of the entire cosmos. Do black holes connect to parallel universes? Einstein's theory of general relativity describes black holes as regions where space-time becomes infinitely curved. This extreme curvature leads to the formation of a singularity. However, some solutions to Einstein's equations suggest that black holes might not always end in a singularity. Instead, they could create pathways through space-time, leading to another part of the universe or even to a completely different universe. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel through space-time. If a black hole is one end of the tunnel, the other end could open into another universe. In this scenario, the black hole wouldn't just destroy everything that falls into it. Instead, the matter and energy might be transported somewhere else entirely. The other end of the wormhole might appear as a white hole, an object that spews out everything that enters the black hole. No evidence of a wormhole has ever been observed, and it's unclear if they could exist in reality. Even if they do, maintaining a stable wormhole would likely require exotic forms of matter or energy that haven't been discovered. This exotic matter would need to counteract the intense gravitational forces trying to collapse the wormhole, keeping it open long enough for something to pass through. The multiverse is the idea that our universe is just one of many, each with its own set of physical laws and properties. If black holes can create or connect to other universes, they could serve as bridges within the multiverse, linking different regions of reality. This would mean that black holes aren't just objects within our universe, but also gateways to a much larger and more complex structure. Black holes are so far away and so extreme in their properties that studying them directly is nearly impossible. Even with advanced telescopes and techniques, we can only observe the effects of black holes on their surroundings. The event horizon hides everything that happens inside, making it hard to gather evidence for what might lie beyond. Some scientists think that indirect evidence could provide clues. For example, if a black hole were connected to another universe, it might leave subtle signatures in the way it interacts with matter and energy. The radiation emitted by the black hole, the behavior of particles near the event horizon, or the gravitational waves it produces could all contain hints about what's happening inside. Detecting these signatures would be a major breakthrough, offering the first glimpse into the possibility of parallel universes. By using advanced mathematical models, scientists can test different scenarios for how black holes might behave and what they could connect to. These models often rely on concepts from quantum mechanics, string theory, and other areas of physics that deal with the fundamental nature of reality. While these theories are complex and sometimes controversial, they provide a framework for thinking about black holes in new and creative ways. If black holes can connect to other universes, what does that mean for our understanding of existence? Are these other universes completely separate, or could they interact with ours in subtle ways? Could life exist in these alternate realities, shaped by different physical laws? Ringdown radiation, the black hole's death cry. When two black holes collide, the event is one of the most violent occurrences in the universe. The immense gravitational forces distort space-time in extraordinary ways, creating ripples that spread outward at the speed of light. These ripples are called gravitational waves, and their discovery has opened a new window into understanding black holes. One of the most fascinating phenomena associated with such events is ringdown radiation, often described as the death cry of a black hole merger. Ringdown radiation occurs in the final stages of a black hole collision, After the two black holes merge, they form a single, larger black hole that is initially unstable. This new black hole vibrates and oscillates as it settles into its final shape. These oscillations produce gravitational waves that carry away the energy from the merger. This process, known as the Ringdown phase, is brief but packed with information. The waves emitted during this phase provide a unique fingerprint of the newly formed black hole. The energy released during a black hole merger is almost unimaginable. In just a fraction of a second, the amount of energy radiated as gravitational waves can exceed the combined output of all the stars in the observable universe. Yet, this energy travels through space-time almost silently, detectable only as tiny distortions that require the most advanced instruments to observe. The vibrations of the black hole during the Ringdown phase are not random. They follow specific patterns determined by the properties of the black hole, such as its mass and spin. These vibrations are often compared to the ringing of a bell. Just as the sound of a bell depends on its size and shape, the gravitational waves produced during the Ringdown reveal details about the black hole. By studying these waves, scientists can learn about the structure and behavior of the black hole in ways that were impossible before. The discovery of gravitational waves was a groundbreaking moment for physics. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. The signal, named GW150914, came from the merger of two black holes located over 1 billion light-years away. Among the data collected from this event was evidence of Ringdown radiation. This marked the beginning of a new era in studying black holes, where scientists could not only observe their effects on surrounding matter, but also listen to their gravitational echoes. General relativity predicts how black holes should behave, including the specific frequencies and patterns of gravitational waves they produce during the Ringdown phase. By comparing these predictions with actual observations, scientists can confirm or challenge the theory. So far, the data from LIGO and other observatories have matched Einstein's predictions remarkably well, reinforcing the theory's accuracy. If the observed gravitational waves differ from what the theory predicts, it could indicate that our understanding of black holes and gravity is incomplete. Such a discovery would have profound implications, potentially pointing to new physics beyond general relativity. There is the possibility that Ringdown radiation might reveal the existence of exotic objects that mimic black holes. Some theories propose the existence of gravastars or other alternatives to black holes. These objects would produce gravitational waves that differ subtly from those of true black holes. By carefully analyzing Ringdown signals, scientists hope to distinguish between black holes and these exotic alternatives. When two black holes merge, the resulting black hole is often much larger than either of the original ones. The energy released during the collision is enormous, with a portion of it converted into gravitational waves. By measuring the energy and frequency of the Ringdown radiation, scientists can estimate the size and spin of the newly formed black hole. This information helps build a clearer picture of how black holes evolve over time and how they influence their surroundings. One challenge in studying Ringdown radiation is that it is relatively faint compared to the earlier stages of a black hole merger. The strongest gravitational waves are produced during the final moments before the two black holes collide, when their orbits rapidly decay. By the time the Ringdown phase begins, much of the energy has already been released. Detecting and analyzing these weaker signals requires highly sensitive equipment and sophisticated techniques. LIGO and its European counterpart, Virgo, have undergone upgrades to improve their sensitivity, allowing them to detect more events and capture fainter signals. In the future, new observatories like the Laser Interferometer Space Antenna, or LISA, will provide even greater capabilities. Operating in space, LISA will be able to detect gravitational waves from mergers involving supermassive black holes, opening up a new frontier in the study of Ringdown radiation. Rejuvenated black holes. Can they be brought back to life? Black holes are often thought of as the ultimate one-way destinations in the universe, pulling in everything that crosses their event horizons. Over time, however, black holes are believed to slowly lose energy through a process called Hawking radiation. This phenomenon, proposed by physicist Stephen Hawking in 1974, suggests that black holes emit tiny amounts of radiation, leading to a gradual loss of mass. But what if, instead of fading away into nothingness, a black hole could somehow be brought back to life? Could they regain mass and energy, defying their seemingly inevitable end? According to quantum mechanics, even the vacuum of space isn't truly empty. It's a seething field of virtual particles constantly popping into and out of existence. These particle pairs usually annihilate each other almost instantly, leaving no trace. However, near the event horizon of a black hole, something unusual can happen. If one particle of a pair falls into the black hole while the other escapes, the escaping particle becomes real, carrying energy away from the black hole. Over immense spans of time, this slow leakage of energy causes the black hole to shrink. For large black holes, the rate of Hawking radiation is incredibly small. A black hole with the mass of a star loses energy so slowly that it would take far longer than the current age of the universe to evaporate completely. But for smaller black holes, the process is much faster. Tiny black holes, sometimes called primordial black holes, could evaporate relatively quickly, releasing their energy in dramatic bursts. If such black holes exist, they may already have disappeared or be in their final stages of evaporation. This leads to the question, can a black hole reverse this process and regain mass? Theoretically, a black hole can grow if it encounters new material to consume. This could be gas, dust, stars, or even other black holes. When matter falls into a black hole, its mass increases and the black hole becomes larger. This process is not uncommon in the universe. Supermassive black holes at the centers of galaxies often gain mass by feeding on the material surrounding them. This is what powers active galactic nuclei and quasars, some of the brightest objects in the universe. But what about a black hole that has been steadily losing mass through Hawking radiation? Could it find a way to regain enough material to counteract its losses? For small black holes, this would be challenging. The amount of matter required to offset the energy loss from Hawking radiation increases as the black hole shrinks. A small black hole would need a constant and substantial source of material to avoid disappearing completely. In the vast emptiness of space, such a supply is unlikely, making rejuvenation a difficult prospect. However, there are scenarios where a black hole might encounter a fresh source of mass. For instance, in dense regions of space, like the centers of galaxies or stellar nurseries, a black hole might encounter clouds of gas or stars. If the black hole's gravitational pull is strong enough, it could begin to consume this material, effectively halting or even reversing its evaporation. Similarly, black holes that wander through regions with a high density of dark matter could theoretically absorb some of this mysterious substance, though the exact mechanics of how dark matter interacts with black holes remain uncertain. There's also the possibility of artificial rejuvenation. Some theoretical discussions have considered whether advanced civilizations could intentionally feed black holes. In such a scenario, a black hole could be used as an energy source, with matter deliberately funneled into it to create bursts of energy. This idea is tied to concepts like the Dyson sphere or other megastructures, where a civilization harnesses the energy of astronomical objects. Feeding a black hole would increase its mass, potentially prolonging its existence and creating a stable source of power. Cosmic strings are hypothetical objects that could stretch across vast distances in the universe, carrying immense amounts of energy. If a black hole were to encounter a cosmic string, the energy transfer could rejuvenate the black hole, increasing its mass and energy. Similarly, some theories suggest that black holes might interact with the vacuum energy of space itself, though these ideas remain speculative. A black hole's ability to gain or lose mass depends on its environment, the availability of material, and the interplay of quantum and gravitational forces. If a black hole gains mass after losing it, does it change in any fundamental way? Does the process affect the information stored in the black hole, or does it remain consistent with the principles of quantum mechanics? Black holes are dynamic, interacting with their surroundings in complex ways. They can grow, merge, evaporate, and possibly even be revived under the right conditions. Understanding these processes could provide new insights into the nature of gravity, quantum mechanics, and the evolution of the cosmos. Magnetic chaos around black holes, the role of relativistic jets. Relativistic jets, which are narrow beams of particles traveling at nearly the speed of light, extend far into space, sometimes stretching across entire galaxies. The connection between these jets, magnetic fields, and the black holes they originate from is a complex and fascinating area of study. At the heart of this phenomenon lies the interaction between a black hole and the surrounding material in its accretion disk. The accretion disk is made up of gas, dust, and other debris spiraling into the black hole under the pull of gravity. As this material moves closer to the event horizon, it becomes incredibly hot and dense, emitting radiation that can be observed across the electromagnetic spectrum. However, this process is not just about gravity. Magnetic fields play a crucial role in organizing and energizing the matter in the disk. Magnetic fields around black holes are generated by the movement of charged particles in the accretion disk. These fields can become twisted and tangled due to the intense gravitational forces and the rapid rotation of the disk. The spinning black hole itself, if it has angular momentum, can further distort and amplify these fields through a process known as the Blandford-Zanajek mechanism. This mechanism suggests that the rotation of the black hole, combined with the strong magnetic fields, can extract energy from the black hole and channel it into the jets. Relativistic jets are among the most dramatic outcomes of this process. These jets are composed of particles, mainly electrons and positrons, accelerated to near-light speeds. They are turned into narrow beams by the magnetic fields, which act like cosmic railways guiding the particles outward. The jets emerge perpendicular to the plane of the accretion disk and can travel vast distances, sometimes extending hundreds of thousands of light-years into intergalactic space. They can carry away more energy than the radiation from the accretion disk itself, and their influence can be felt far beyond the immediate vicinity of the black hole. When these jets collide with the surrounding interstellar medium, they create shock waves that heat the gas and trigger the formation of enormous bubbles of plasma. These structures, known as radiolobes, can be observed in many galaxies with active black holes, including quasars and radiogalaxies. On a larger scale, they play a significant role in galaxy evolution. The energy and momentum carried by the jets can regulate the growth of galaxies by influencing the gas that fuels star formation. In some cases, the jets can sweep away gas from the central regions of a galaxy, preventing it from cooling and collapsing into new stars. This process, known as feedback, is thought to be one of the key mechanisms that link the growth of supermassive black holes to the evolution of their host galaxies. Observations and simulations suggest that the magnetic fields are highly organized near the black hole, but become more chaotic as the jets travel outward. This chaotic behavior can lead to the formation of instabilities and turbulence within the jets, which can influence their shape and energy distribution. Despite this complexity, the jets manage to remain remarkably focused over vast distances, a testament to the strength and persistence of the magnetic fields guiding them. Unlike light or particles, magnetic fields do not travel through space in a way that can be directly detected. Instead, scientists infer their presence and properties by studying their effects on the surrounding matter and radiation. For example, the polarization of light emitted by the accretion disk and jets can provide clues about the orientation and strength of the magnetic fields. Similarly, high-resolution imaging of jets in radio wavelengths can reveal their structure and influence. Why do some black holes produce powerful jets while others remain relatively quiet? One possibility is that the spin of the black hole plays a critical role. Faster spinning black holes are thought to be more efficient at extracting energy through the Blandford-Znajek mechanism, leading to more powerful jets. The amount and configuration of the surrounding material may also influence jet formation, as a dense and turbulent accretion disk can amplify magnetic fields and provide more particles for the jets. While supermassive black holes in the centers of galaxies are the most visible producers of relativistic jets, smaller black holes, such as those formed from the collapse of massive stars, can also generate jets under the right conditions. The underlying physics appears to be similar across a wide range of black hole masses, suggesting that the interplay of gravity, magnetism, and particle acceleration is a universal feature of these objects. In recent years, advances in observational technology have provided new insights into these phenomena. Telescopes like the Event Horizon Telescope and the Very Large Array have captured detailed images of jets and the regions near black holes, offering a closer look at the structures and processes involved. Meanwhile, computer simulations have allowed researchers to model the behavior of magnetic fields and jets with increasing accuracy, revealing patterns and interactions that were previously hidden. The precise mechanisms that generate and sustain the magnetic fields around black holes are not fully understood, nor is the process by which these fields interact with the black hole's spin and the accretion disk. The dynamics of the jets themselves, including their stability and the way they transfer energy to their surroundings, also continue to puzzle scientists. Each new discovery seems to open the door to further questions, underscoring the complexity and richness of these cosmic phenomena. Black hole echoes, a possible clue to quantum gravity. Gravitational wave echoes, if they exist, could carry information about the quantum nature of black holes, potentially offering clues to the long-sought theory of quantum gravity. Gravitational waves themselves are now a well-established phenomenon, but the idea of echoes in gravitational waves takes things a step further, suggesting there might be something beyond Einstein's framework waiting to be uncovered. According to general relativity, the region beyond a black hole's event horizon is entirely cut off from the rest of the universe. However, some theories that attempt to combine quantum mechanics with gravity propose that this picture might not be entirely accurate. One idea is that the event horizon of a black hole might not be a smooth, featureless surface. Instead, it could be surrounded by a complex structure influenced by quantum effects. This structure might reflect some of the gravitational waves that strike it, creating a series of faint echoes that follow the initial wave. These echoes would occur because the gravitational waves would bounce back and forth between the black hole's quantum structure and the surrounding space-time before eventually fading away. Detecting these echoes is an incredibly challenging task. The signals are expected to be extremely weak and buried in noise. Gravitational wave detectors like LIGO and Virgo are already working at the limits of sensitivity, and the echoes, if they exist, would require even more precise measurements. Researchers have developed sophisticated techniques to search for these faint patterns, but so far, the results have been inconclusive. Some studies have reported hints of echoes in the data, while others have found no evidence. Gravitational wave echoes would provide direct evidence that black holes are not the simple objects described by general relativity, but instead have a more complex quantum nature. This would be a major step toward understanding how gravity and quantum mechanics interact. The echoes could offer insights into the behavior of space-time at its most extreme, revealing details about phenomena like the quantum structure of the event horizon or the possibility of alternative theories of gravity. One of the leading ideas in this area is the concept of quantum hair, which suggests that black holes might retain subtle traces of the matter and energy that fell into them, encoded in quantum fluctuations near the event horizon. The quantum hair could interact with gravitational waves, producing the echoes that researchers are searching for. Testing this idea requires not only detecting the echoes, but also analyzing their patterns to see if they match the predictions of quantum Hare models. Another possibility is that the echoes could be related to the existence of a firewall. Gravitational wave echoes could provide a way to test this theory, as the presence of a firewall might reflect and scatter the waves in distinctive ways. Some theories suggest that black holes might be connected to other regions of spacetime through things like wormholes. If such exotic structures exist, they could leave subtle imprints on the gravitational waves produced during black hole mergers. Echoes might be one way to detect these effects, providing a window into the hidden dimensions of the cosmos. To make progress in this area, scientists are not only improving the sensitivity of gravitational wave detectors, but also developing new methods for analyzing the data. Machine learning and advanced statistical techniques are being used to search for patterns that might indicate the presence of echoes. Wandering black holes, homeless giants in intergalactic space. Unlike most black holes, which are anchored within galaxies, wandering black holes drift through intergalactic space, untethered and alone. Their existence challenges our understanding of cosmic dynamics and raises questions about how such massive objects can become homeless in a universe dominated by gravity's pull. The journey of a wandering black hole often begins with a violent event. One common cause is a galactic collision or merger. When two galaxies interact, their central black holes can form a binary system, orbiting each other as the galaxies merge. If a third massive object, such as another black hole, becomes involved, the gravitational interactions can become chaotic. In some cases, one of the black holes in the system may be flung outward with enough force to escape the gravitational pull of the newly formed galaxy. This gravitational slingshot sends the black hole hurtling into intergalactic space. Another potential origin for rogue black holes is the aftermath of a black hole merger. When two black holes collide, they release a tremendous amount of energy in the form of gravitational waves. This energy is not always emitted symmetrically, which can create a recoil effect. The resulting kick can propel the newly formed black hole at high speeds, sometimes fast enough to escape the gravitational hold of its host galaxy. The magnitude of this kick depends on factors such as the masses and spins of the merging black holes and the angle at which they collide. Once ejected, a wandering black hole becomes a solitary traveler. Intergalactic space is vast and empty, with only trace amounts of gas and dust scattered across incomprehensible distances. For a black hole, this means a significant reduction in the amount of material it can accrete. Without a steady supply of matter to consume, the black hole becomes much harder to detect. It no longer produces the bright emissions of light and radiation that are characteristic of active black holes within galaxies. Instead, it becomes a dark, silent presence, detectable only through its gravitational influence. Despite their elusive nature, wandering black holes are thought to be relatively common. The sheer number of galaxies in the universe, combined with the frequency of galactic mergers and interactions, suggests that there could be millions of rogue black holes drifting through intergalactic space. These black holes range in size from stellar mass black holes, formed from the collapse of massive stars, to supermassive black holes, which can weigh millions or billions of times more than the Sun. The latter are particularly intriguing, as their ejection requires extreme conditions and immense gravitational forces. While these objects are often far removed from other matter, their gravitational pull can still have effects. For instance, if a rogue black hole were to pass through a dense region of gas or a cluster of stars, it could disrupt the motion of nearby objects, creating ripples in the structure of the affected region. In rare cases, a wandering black hole might even capture a star, forming a temporary accretion disk and emitting a brief flare of radiation before returning to its silent journey. As these objects travel through space, they may occasionally encounter clouds of gas and dust. While the amount of material accreted is likely small compared to the activity within galaxies, it could still contribute to the heating and ionization of the intergalactic medium over time. This process may have subtle but significant effects on the evolution of the universe, influencing the formation of new structures and the behavior of cosmic matter on large scales. Without the bright emissions associated with accretion, these objects are effectively invisible to traditional telescopes. However, their gravitational influence offers a potential method of discovery. Rogue black holes can cause gravitational lensing, bending the light from distant stars and galaxies as it passes through their gravitational field. By carefully analyzing these distortions, astronomers can infer the presence and properties of a black hole. This technique has already been used to detect other compact objects, such as isolated neutron stars, and holds promise for identifying rogue black holes as well. If a rogue black hole were to pass close enough to a star, it could capture or disrupt the star, producing a tidal disruption event. These events generate a burst of light and radiation as the star is torn apart, providing a temporary beacon that can be detected by telescopes. Unlike stars or planets, black holes do not have a defined lifespan. They persist indefinitely, gradually losing mass through the slow process of Hawking radiation. For stellar mass black holes, this process takes far longer than the current age of the universe, making them effectively eternal from a human perspective. Supermassive black holes with their immense mass take even longer to evaporate. As a result, wandering black holes are likely to remain as silent witnesses to the universe's evolution for eons to come. The study of wandering black holes is still in its early stages, but these objects challenge our assumptions about the behavior and dynamics of massive celestial bodies, offering new insights into the forces that shape galaxies and the intergalactic medium. The holographic principle. Are black holes the ultimate data storage? Black holes could be the ultimate data storage devices, capable of encoding vast amounts of information on their surfaces. This concept is tied to the holographic principle. In the 1970s, physicist Jacob Bekenstein proposed that the amount of information a black hole can contain isn't proportional to its volume, as one might expect, but to the surface area of its event horizon. This was a radical departure from conventional thinking. In most physical systems, the amount of information or entropy is related to the volume. But black holes don't follow the same rules. Instead, their entropy scales with the area of their event horizon, not the space inside. The holographic principle suggests that all the information about the matter that falls into a black hole is somehow encoded on its surface, or event horizon, in the form of tiny quantum bits. These bits are like pixels on a screen, storing the data in a way that preserves it, even as the black hole evolves. This means that the three-dimensional space inside the black hole could be described entirely by the two-dimensional surface of its event horizon. It's as if the black hole is a giant cosmic hard drive, with its data written on the surface for the universe to read. If only we had the tools to decode it. Some physicists believe the holographic principle could apply to the entire universe. According to this idea, everything we experience in 3 dimensions might be a kind of projection from a 2-dimensional surface at the edges of the cosmos. In other words, the universe could be a hologram, where the real information exists on a distant boundary, and what we see as depth and volume is an illusion. This doesn't mean the universe isn't real, but it does suggest that reality might work very differently from how we perceive it. If all the information about a black hole's interior is stored on its surface, it raises questions about what inside really means. The interior of a black hole might not be a separate region of space at all, but a kind of projection from the event horizon. This challenges the traditional view of space-time as a smooth, continuous fabric, and suggests that at the smaller scales, space and time might be made up of discrete units, like pixels on a screen. Some researchers are exploring how quantum mechanics and gravity interact at the event horizon. These efforts aim to uncover the code that governs black holes and, by extension, the universe itself. If we can figure out how information behaves in such extreme conditions, it could lead to breakthroughs in our understanding of quantum gravity. Black holes are incredibly efficient at storing information, packing it into the smallest possible space. Studying how they do this could inspire new technologies for data storage and processing. For example, researchers are already using concepts from black hole physics to develop quantum algorithms and encryption methods. These applications might one day revolutionize how we handle information on Earth, just as black holes revolutionize our understanding of it in the cosmos. If information is encoded on the event horizon, then it might be possible to recover it from the Hawking radiation emitted by the black hole. This would mean that black holes don't destroy information after all, but merely transform it into a different form. Recent studies suggest that the patterns of Hawking radiation might carry subtle imprints of the information encoded on the event horizon, offering a way to test this idea experimentally. If the event horizon shrinks over time, does the encoded information become compressed, or is it gradually released into the universe? And if the black hole eventually disappears completely, does the information survive in some other form? How exactly is the information encoded on the event horizon in the first place? Some theories propose that it's stored in the form of quantum entanglement, where particles are linked in such a way that the state of one particle depends on the state of another, no matter how far apart they are. Others suggest that the information is encoded in tiny fluctuations of space-time itself, known as quantum geometry. These ideas are still highly speculative, and testing them requires advances in both theory and technology. Polarized light and the secrets of a black hole's magnetic field. The light that reaches us from the vicinity of black holes contains hidden messages about the forces at play around them, especially the magnetic fields that shape their behavior. One of the key ways scientists uncover these secrets is by studying the polarization of light emitted near black holes. Light is a form of electromagnetic radiation, and it oscillates as it travels. Usually, the oscillations happen in all directions perpendicular to the light's path. However, when light becomes polarized, these oscillations are restricted to a specific direction. Polarization can occur for several reasons, such as when light scatters off particles, passes through certain materials, or interacts with strong magnetic fields. Near black holes, polarization often results from the interaction of light with charged particles in the accretion disk and the powerful magnetic fields that thread through it. As matter falls toward a black hole, it heats up to millions of degrees, emitting radiation across the electromagnetic spectrum. The magnetic fields within the disk play a crucial role in controlling the movement of this matter. These fields can guide the charged particles, influence the formation of relativistic jets, and regulate how energy is transported within the disk. By studying the polarization of light emitted from these regions, scientists can map the structure and strength of the magnetic fields, offering a rare window into the processes occurring so close to the black hole. One of the tools used to study polarization is a type of telescope equipped with polarimeters, instruments designed to measure the direction and degree of light's polarization. The Event Horizon Telescope, or EHT, which famously captured the first image of a black hole's shadow in 2019, also observed polarized light from the black hole at the center of the galaxy M87. This data provided groundbreaking insights into the magnetic fields near the event horizon. The polarization patterns revealed that the magnetic fields in this region were highly organized, forming loops that aligned with the black hole's rotation. This suggested that the magnetic fields were strong enough to resist being completely tangled by the turbulent motion of the accretion disk. These findings also shed light on the origins of the powerful jets that some black holes emit. The polarized light from M87's black hole suggested that the magnetic fields near the event horizon were strong enough to channel the energy and particles into narrow, focused beams, providing crucial evidence for theories of jet formation. Black holes emit radiation across the electromagnetic spectrum, from radio waves to X-rays, and polarization can occur in all these wavelengths. X-ray polarization in particular is a powerful tool for probing the innermost regions of the accretion disk, where the gravitational forces are strongest. In these regions, the light's polarization can reveal how the disk's matter flows, how energy is dissipated, and how the magnetic fields interact with the black hole's rotation. Future X-ray polarimetry missions aim to provide even more detailed maps of these extreme environments. According to relativity, the intense gravity near a black hole should warp space and time, bending the paths of light rays and causing the light to become polarized in specific ways. By comparing the observed polarization patterns with theoretical predictions, scientists can look for deviations that might hint at new physics. So far, the data has been consistent with general relativity, but each new observation pushes the boundaries of our understanding and tests the theory in ever more extreme conditions. Despite the progress made so far, many questions remain. One mystery is how the magnetic fields become so strong and organized in the first place. Theoretical models suggest that the motion of charged particles in the accretion disk amplifies the magnetic fields through a process called the magneto-rotational instability. However, the details of this process are still being explored, and it's unclear how it operates in the extreme conditions near a black hole. Another open question is the role of magnetic reconnection, a phenomenon where magnetic field lines break and reconnect, releasing vast amounts of energy. This process is thought to occur in the turbulent regions of the accretion disk and may play a role in heating the disk and accelerating particles in the jets. Observing the signatures of magnetic reconnection in polarized light could provide valuable clues about how energy is transferred and dissipated. Time travel through wormholes, a black hole connection. Einstein-Rosen bridges, or wormholes, were first proposed in 1935 by Albert Einstein and Nathan Rosen. They described a tunnel-like structure where at one end of the tunnel, matter or light could enter, travel through the bridge, and emerge at the other end, potentially in a different location or even a different time. While wormholes are mathematical solutions to Einstein's equations of general relativity, whether they exist in reality is another question entirely. Black holes bend space-time to extreme degrees. In some theoretical models, a black hole could form one end of a wormhole. The other end might be another black hole, a white hole, or a completely different region of space-time. If such a connection exists, it might provide a pathway through space-time. According to relativity, time flows differently near massive objects due to gravitational time dilation. A clock near a black hole would tick more slowly compared to one far away. If one end of a wormhole were placed near a black hole, where time moves slowly, and the other end were in a region with normal time flow, traveling through the wormhole could allow someone to effectively move forward or backward in time. However, wormholes, if they exist, would be inherently unstable. They would collapse almost instantly after forming, preventing anything from passing through. To keep a wormhole open, it would require a substance with negative energy density, often referred to as exotic matter. This kind of matter is not something we've observed in nature, though certain quantum effects hint that it might exist in tiny amounts. Even if exotic matter could be harnessed, the amount needed to stabilize a wormhole would be enormous, far beyond our current technological capabilities. The immense gravitational forces near a black hole's event horizon would also likely destroy anything attempting to enter it. Theoretical wormholes would need to avoid this destructive environment, requiring precise conditions that may be impossible to achieve naturally. Even if a stable wormhole could exist, navigating it would be extraordinarily complex, as any small disturbance could collapse the structure or send the traveler to an unintended destination. Time travel through wormholes could lead to paradoxes, such as the classic grandfather paradox, where someone traveling to the past could interfere with events in a way that prevents their own existence. Resolving these paradoxes would require a deeper understanding of the laws of physics, particularly the relationship between general relativity and quantum mechanics. Some theories suggest that quantum effects might prevent paradoxes by enforcing a kind of self-consistency, where events unfold in a way that avoids contradictions. Advances in our understanding of quantum gravity might shed light on whether wormholes are more than just mathematical curiosities. Some researchers have explored the possibility that microscopic wormholes could form at quantum scales, providing a potential bridge between the macroscopic world of relativity and the microscopic realm of quantum mechanics. These tiny wormholes wouldn't be large enough for a person to travel through, but they could still have profound implications for our understanding of the universe. Observations of black holes are giving us unprecedented views of their structure and behavior. While these observations haven't revealed direct evidence of wormholes, they are helping scientists refine their models and test predictions. Some theories propose that the intense conditions shortly after the Big Bang might have created primordial wormholes. These structures could still exist today, hidden in the vastness of space. Detecting one of these ancient wormholes would be a monumental task, requiring instruments capable of identifying their unique gravitational or electromagnetic effects. Negative energy and the role of exotic matter. Near black holes. Exotic matter refers to a hypothetical type of material that behaves in ways fundamentally different from the matter we encounter daily. Its unique properties, such as having negative energy density, are crucial for the theoretical stability of structures like wormholes. Wormholes are predicted to collapse almost instantly due to gravitational forces unless some form of support can counteract the intense pull of gravity. This is where exotic matter with its negative energy comes into play. Negative energy creates a kind of repulsive force, acting against the natural tendency of the wormhole to close. By introducing enough exotic matter into the structure, the wormhole might remain open long enough for something or someone to pass through. In the realm of quantum physics, negative energy has a basis in real phenomena. One example is the Casimir effect, where two closely placed uncharged metal plates in a vacuum experience an attractive force due to quantum fluctuations. These fluctuations create a situation where the energy between the plates is less than the energy outside them, effectively producing a region of negative energy density. While this effect is minuscule and observed only at microscopic scales, it demonstrates that negative energy is more than just a mathematical idea. Scaling this concept up to something as vast as a wormhole or a black hole presents enormous challenges. The amount of negative energy required to stabilize a wormhole would be astronomical, far beyond what we can generate. Moreover, the conditions needed to produce and sustain exotic matter are unknown. If such matter exists naturally, it might be incredibly rare, possibly forming only under the most extreme circumstances, such as near black holes or in the early universe. Theoretical physicists have speculated about how exotic matter might behave near a black hole. One possibility is that the intense gravitational fields around a black hole could create conditions conducive to the formation of negative energy. For instance, as particles fall into a black hole, quantum effects might generate negative energy in specific regions, particularly near the event horizon. This process could theoretically affect the dynamics of the black hole, influencing how it interacts with its surroundings, or even with a connected wormhole. Hawking radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs are created. Some theories suggest that negative energy might be involved in this process, further connecting exotic matter to black hole behavior. If exotic matter could stabilize a wormhole, where would that wormhole lead? Would it connect two regions of our universe, or could it serve as a bridge to another universe entirely? In either case, the presence of exotic matter would likely leave observable traces. For instance, The interaction between exotic matter and the intense gravitational forces near a black hole might produce unique signals. Detecting them would be an important step in confirming the existence of exotic matter. If regions of negative energy exist near black holes, they could alter the way matter and energy are drawn into the black hole. This might affect the black hole's spin, mass, or even its shape. Understanding these interactions could provide new insights into the life cycles of black holes. Theoretical models suggest that even the smallest stable wormhole would require a staggering amount of exotic matter. Additionally, exotic matter's properties might make it difficult or impossible to manipulate. If it has negative mass, for example, it could behave in ways that defy our current understanding of physics, such as accelerating away when pushed. These challenges highlight how much we still have to learn about the fundamental nature of the universe. Despite the hurdles, the study of exotic matter and negative energy remains a vital part of modern physics. It pushes the boundaries of what we know, forcing scientists to explore the intersection of general relativity, quantum mechanics, and cosmology. While we may not yet have the tools to fully investigate these phenomena, advancements in technology and theoretical frameworks continue to bring us closer to answers. Exotic matter and negative energy sit at the crossroads of quantum field theory and general relativity. By studying these concepts in the extreme environments around black holes, scientists hope to uncover clues that could lead to a deeper understanding of the universe's underlying laws. If exotic matter can stabilize wormholes, it might allow for the existence of multiverse-like structures, where different regions of spacetime are connected in ways we can only begin to imagine. Black hole mergers when titans collide. When two black holes draw close to one another and merge, the result is not just the union of two gravitational giants, but the release of energy on a scale that's hard to comprehend. In many cases, black holes that eventually merge started as part of binary star systems. These systems consist of two stars orbiting each other, bound together by gravity. If both stars are massive enough, they may each end their lives in a supernova, leaving behind two black holes. Over time, the orbit of these black holes can shrink due to a process called gravitational radiation. As they lose energy, they spiral closer together, setting the stage for their eventual merger. Over millions or even billions of years, they move closer together as gravitational waves carry away their orbital energy. As the black holes get closer, the effects of their interaction become more dramatic. The gravitational waves grow stronger, carrying more energy away from the system and causing the black holes to spiral inward faster. As they approach each other, their immense gravitational fields distort spacetime to an extreme degree. The energy released in these moments is staggering, far surpassing the combined light output of all the stars in the observable universe. Yet this energy is not released as light or heat, but as gravitational waves. These waves travel outward from the merging black holes, spreading through spacetime, and eventually reaching detectors on Earth. When the black holes finally collide, they form a single, larger black hole. The new black hole is not immediately stable. It vibrates and oscillates. During this ringdown phase, the black hole emits additional gravitational waves as it settles into its final state. One of the remarkable aspects of black hole mergers is the variety of systems they reveal. Some involve relatively small black holes, with masses a few times that of the Sun. Others feature much larger black holes, with masses tens or even hundreds of times greater. In some cases, the black holes are nearly identical in size, while in others, one is significantly larger than the other. These differences affect the dynamics of the merger and the properties of the resulting gravitational waves. Some observed mergers involve black hole spins that are misaligned with their orbital motion, suggesting complex formation histories that may involve interactions with other objects or chaotic environments. The newly formed black hole is larger than either of its progenitors, but not as massive as their combined weight. This is because a significant portion of the system's mass is converted into energy and carried away by gravitational waves during the merger. The spin of the new black hole is determined by the spins of the original black holes and the dynamics of their collision. In some cases, the resulting black hole may be spinning so rapidly that it approaches the theoretical limit set by relativity. Black hole mergers can influence their surroundings in subtle but significant ways. For instance, the energy released as gravitational waves can affect nearby matter, and the merged black hole may receive a kick that propels it out of its original location. In some cases, this kick could eject the black hole from its host galaxy, leaving it wandering through intergalactic space. Many black holes are found in the centers of galaxies, where they can form binary systems and eventually merge. These events may play a role in shaping the evolution of galaxies, influencing the distribution of stars and the behavior of gas and dust. Could artificial black holes be created in a lab? The idea of creating artificial black holes in a laboratory setting is a concept that bridges science fiction and cutting-edge theoretical physics. Theoretical discussions about artificial black holes focus on small, manageable versions of these cosmic phenomena, far removed from the monstrous black holes that exist in space. These artificial black holes would be tiny, possibly microscopic, but still governed by the same fundamental principles as their larger counterparts. The primary motivation for attempting to create artificial black holes is to study their properties in a controlled environment. Black holes hold the key to some of the most profound questions in physics. By producing a black hole in the lab, scientists could observe how it interacts with matter and energy up close, offering insights that are impossible to gain from observing distant cosmic black holes. Theoretical proposals for creating artificial black holes often involve the use of extreme energy densities. According to general relativity, a black hole forms when matter is compressed into a sufficiently small volume, creating a gravitational field so intense that not even light can escape. On a microscopic scale, this means concentrating an enormous amount of energy into an incredibly small space, a feat that requires technology far beyond our current capabilities. Particle accelerators, such as the Large Hadron Collider, or LHC, have been mentioned in discussions about creating artificial black holes. These machines are capable of accelerating particles to nearly the speed of light and smashing them together with immense energy. Some theories suggest that if the energy of these collisions were high enough, they could create conditions similar to those present during the early moments of the universe, potentially leading to the formation of tiny black holes. However, these black holes would be incredibly small, with masses on the order of a few micrograms or less. They would also evaporate almost instantly due to Hawking radiation. In the case of microscopic black holes, this evaporation would happen so quickly that they would pose no danger to their surroundings. The energy required to produce such a black hole is far beyond what current technology can achieve. The LHC, for instance, operates at energies on the order of tera-electron volts, which is impressive, but still far short of the levels needed to create a black hole. Some theories of extra dimensions, however, suggest that if additional spatial dimensions exist, they could lower the energy threshold for black hole formation, making it more achievable with current or near-future technology. The possibility of extra dimensions comes from string theory, a framework that attempts to unify quantum mechanics and general relativity. In some versions of string theory, our universe is just one of many three-dimensional surfaces within a higher dimensional space. If these extra dimensions exist, they could affect how gravity behaves at small scales, potentially allowing black holes to form at lower energy levels than previously thought. This idea has generated excitement, but remains speculative, as there is no direct evidence for the existence of extra dimensions. Advanced laser systems, such as those used in high-energy physics experiments, can produce incredibly focused beams of energy. By concentrating these beams onto a tiny point, it might be possible to achieve the energy densities required to form a black hole. This approach is still theoretical, but it highlights the creative ways scientists are thinking about the problem. While microscopic black holes would evaporate almost instantly, some have expressed concerns about the potential risks of such experiments. These concerns were famously raised during the commissioning of the LHC, with fears that it might create a black hole capable of growing and consuming the Earth. However, extensive safety analyses conducted by physicists have shown that these fears are unfounded. Natural processes, such as cosmic ray collisions in the Earth's atmosphere, occur at much higher energies than those produced in the LHC, yet they have never resulted in the formation of a dangerous black hole. Even if the technical and safety challenges could be overcome, the question remains, what could we learn from artificial black holes? One possibility is gaining a deeper understanding of Hawking radiation. Observing this phenomenon in a laboratory setting would provide direct evidence for a process that has so far only been theorized. It could also offer insights into the quantum properties of black holes, helping to bridge the gap between quantum mechanics and general relativity. Black holes create conditions where space-time is curved to its limits, offering a natural laboratory for testing theories of gravity. By studying these effects in a controlled environment, scientists could refine their understanding of how gravity works on both large and small scales. Some have suggested that artificial black holes could be used as incredibly efficient energy sources. As matter falls into a black hole, it releases a significant amount of energy in the form of radiation, which could, in theory, be captured and used. This idea remains far-fetched, but it illustrates the potential for black holes to inspire innovative thinking. Shortly after the Big Bang, conditions were so extreme that microscopic black holes may have formed naturally. These primordial black holes could still exist today, hidden in the vastness of space. By studying artificial black holes, scientists could gain insights into the processes that shape the universe in its earliest moments. Does the universe behave like a giant black hole? One of the most striking similarities between the universe and a black hole is the event horizon. For black holes, the event horizon is the boundary beyond which nothing can escape. In the case of the universe, there is a similar boundary known as the cosmic horizon. This is the farthest distance from which light has had time to reach us since the beginning of the universe, about 13.8 billion years ago. The cosmic horizon is not a fixed structure, but rather a consequence of the universe's expansion. Beyond this horizon, the light emitted by distant objects is stretched so much by the expanding space that it can no longer reach us, effectively cutting off our ability to observe those regions. Both horizons serve as limits to what can be known or observed, and this parallel raises intriguing questions. Could the universe's cosmic horizon function like the event horizon of a black hole, marking the boundary of a self-contained system? In some ways, this comparison suggests that the universe might behave as a kind of black hole turned inside out. Instead of matter and energy being drawn inward toward a singularity, as in a black hole, the universe's expansion pushes everything outward, creating an observable horizon that continues to grow. Black holes are regions of space where matter is compressed to an extreme density, creating immense gravitational pull. The universe, at its beginning, also had an incredibly high density. During the first moments after the Big Bang, all the matter and energy in the cosmos were concentrated in a tiny, dense state. This initial condition bears a resemblance to the singularity at the heart of a black hole, where the laws of physics as we know them break down. Some physicists speculate that the Big Bang itself might have been a kind of reverse black hole event, a white hole, expelling matter and energy into a new space-time. In Einstein's theory of general relativity, the shape of space-time is determined by the distribution of matter and energy. Black holes are solutions to Einstein's equations that describe regions where space-time curves inward so steeply that nothing can escape. The universe, on a cosmic scale, is also governed by these equations, with its overall shape influenced by its total mass and energy. current observations suggest that the universe is flat, meaning its geometry is balanced between expansion and collapse. However, this flatness could be seen as analogous to the balance point at the event horizon of a black hole, where space-time is neither fully open nor completely closed. One speculative hypothesis that takes this comparison further is the idea that the universe itself might be a black hole from the perspective of a higher dimensional space. In this view, our three-dimensional universe could be the surface of a four-dimensional black hole, with its event horizon corresponding to the cosmic horizon we observe. This idea is closely tied to theories of higher dimensions and brane cosmology, which propose that our universe exists as a brane embedded in a higher dimensional space. If this is true, then the properties of black holes in our universe might mirror the larger-scale behavior of the cosmos itself. Black holes are known to have enormous entropy. The entropy of a black hole is proportional to the surface area of its event horizon, a discovery that has profound implications for our understanding of thermodynamics and information theory. Similarly, the universe has its own entropy, which has been increasing since the Big Bang. This increase is driven by processes such as star formation, the creation of black holes, and the conversion of matter into radiation. Some physicists speculate that the universe's entropy might eventually reach a maximum state known as the heat death, where no further energy can be extracted from any system. This would be analogous to a black hole reaching a stable state where it no longer absorbs matter or energy. One idea is that black holes within our universe might serve as seeds for new universes. In this scenario, the collapse of matter into a black hole could lead to the formation of a new space-time region, separate from our own. This idea is rooted in the concept of quantum fluctuations and the potential for space-time to behave differently under extreme conditions. If true, it would mean that our universe could itself be the offspring of a black hole in another universe, part of a potentially infinite cycle of cosmic creation. String theories take on black hole mysteries. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. The different modes of vibration of these strings correspond to different particles and forces. This framework provides a way to unify general relativity and quantum mechanics, the two major theories that often conflict when applied to black holes. According to classical physics, anything that falls into a black hole is lost forever once it crosses the event horizon. This poses a problem because it contradicts quantum mechanics, which states that information cannot be destroyed. The evaporation of black holes through Hawking radiation only deepens the mystery. String theory provides a solution through the concept of fuzzballs. In string theory, a black hole is not described as a singularity surrounded by an event horizon, but as a fuzzball. A fuzzball is a complex configuration of strings and branes that spread out and occupy the space where the event horizon would traditionally exist. Instead of a sharp boundary, the surface of a fuzzball is thought to be irregular and dynamic, made up of these fundamental stringy elements. In the fuzzball picture, information about matter that falls into the black hole is not lost, but encoded in the intricate structure of the fuzzball's surface. As the black hole emits radiation, this information is gradually released, ensuring that quantum mechanics remains intact. The fuzzball model challenges the traditional notion of an event horizon as an impenetrable barrier, suggesting instead that the surface of the black hole is more like a holographic screen where information is stored. String theory also reimagines the singularity at the heart of a black hole. In classical general relativity, the singularity is a point of infinite density where space-time curvature becomes infinite. This concept defies physical understanding and creates a breakdown in the laws of physics. String theory, however, replaces the singularity with a dense network of strings and branes. This network spreads out the mass and energy, avoiding the infinities predicted by relativity. This approach aligns with the broader goal of string theory, to smooth out the singularities that arise in traditional models of spacetime. The entropy of a black hole, as described by the famous Bekenstein-Hawking formula, is proportional to the area of its event horizon. String theory provides a microscopic explanation for this entropy by showing that it corresponds to the number of possible configurations of strings and branes that form the black hole. Each configuration represents a different quantum state, and the sheer number of these states accounts for the observed entropy. The success of string theory in explaining black hole entropy is seen as one of its greatest achievements. By linking the macroscopic properties of black holes, such as their entropy and temperature, to the microscopic behavior of strings and branes, it bridges the gap between quantum mechanics and gravity. This breakthrough suggests that string theory may hold the key to understanding the true nature of black holes. String theory predicts the existence of extra dimensions beyond the familiar three of space and one of time. These dimensions are compactified, meaning they are curled up and hidden from everyday observation. Black holes, with their extreme gravitational fields, could provide a way to probe these hidden dimensions. Another aspect of string theory's take on black holes is its prediction of tiny primordial black holes that would have formed in the early universe and could be much smaller than the stellar mass black holes we observe today. Detecting such black holes would provide a direct test of string theory's predictions. One of the main criticisms of string theory is its lack of direct experimental evidence. While the mathematical framework of string theory elegantly describes black holes and resolves many of their mysteries, it remains difficult to test these ideas in a laboratory or through astronomical observations. Nevertheless, the theoretical insights gained from string theory continue to inspire new ways of thinking about black holes and their role in the cosmos. The search for naked singularities. In standard models, a singularity is always hidden behind an event horizon. Naked singularities, on the other hand, are theoretical objects where this boundary does not exist. They expose the singularity to the outside world. General relativity predicts singularities as the end result of gravitational collapse. For most cases, this collapse forms an event horizon, enclosing the singularity and cutting it off from direct observation. However, certain mathematical solutions to Einstein's equations suggest that under specific conditions, the formation of an event horizon might be avoided, leaving the singularity exposed. One of the primary reasons naked singularities are so fascinating is their potential to challenge the cosmic censorship conjecture. Proposed by physicist Roger Penrose in the 1960s, this conjecture suggests that the universe has a way of censoring singularities by ensuring they are always hidden behind event horizons. This idea preserves the predictability of physical laws because singularities, if exposed, could disrupt the structure of space-time in unpredictable ways. If naked singularities exist, they could break this cosmic rule, introducing a level of chaos that defies our current understanding of physics. Physicists have explored several scenarios where naked singularities might form. One involves the collapse of a rotating star. In such a case, the intense spin of the star could create conditions where the event horizon fails to form. Rapid rotation counteracts the inward pull of gravity, potentially allowing the singularity to remain visible. Another scenario involves the collision of two massive objects, where the resulting dynamics could briefly expose a singularity before an event horizon forms around it. In theoretical models, a black hole with a high electric charge could push the limits of what is known as the extremal condition. If the charge-to-mass ratio exceeds a critical value, the event horizon might vanish, leaving the singularity exposed. These scenarios are speculative, as real-world astrophysical processes often involve additional factors, such as magnetic fields and matter interactions, that complicate the picture. One of the most significant consequences of naked singularities would be the breakdown of determinism. In classical physics, the behavior of a system is determined by its initial conditions and the laws governing it. With a naked singularity, this predictability could vanish. The intense gravitational field near the singularity could bend light and matter in unpredictable ways. creating regions of spacetime where cause and effect no longer operate as expected. Near a singularity, the gravitational field becomes so strong that quantum effects cannot be ignored. Observing a naked singularity could provide direct insights into the interplay between these two fundamental forces. It might reveal phenomena that challenge existing theories, or point the way toward new frameworks for understanding the universe. By their nature, singularities represent regions where known physical laws break down, making them difficult to study even in theory. Observationally, detecting a naked singularity would require distinguishing it from other compact objects, such as black holes or neutron stars. This is no easy task, as the behavior of matter and light near these objects can be similar in many ways. Light emitted from near a singularity could be affected by the intense gravitational field, leading to unique polarization patterns. These patterns might differ from those produced near black holes, providing a way to distinguish between the two. Theoretical research continues to explore the conditions under which naked singularities might form. Numerical simulations play a crucial role in this work, allowing physicists to model the behavior of collapsing stars, rotating systems, and other extreme scenarios. These simulations test the limits of the cosmic censorship conjecture and explore the boundary between black holes and naked singularities. While no definitive evidence for naked singularities has yet been found, the search itself is pushing the boundaries of our understanding. Some physicists argue that the concept of a naked singularity might suggest that our current theories are incomplete or that new principles are waiting to be discovered. The existence of naked singularities might indicate that spacetime has a richer and more complex structure than we currently realize. It could point toward hidden symmetries, extra dimensions, or other features that lie beyond the reach of general relativity. Could black holes birth new universes? The cosmic seed hypothesis. While the singularity is often seen as the end of the road for matter and energy falling into a black hole, some theories suggest it might also be a beginning. The conditions near a singularity, extreme density, pressure, and temperature, resemble the state of the universe at the moment of the Big Bang. One of the frameworks that support this idea is bounce cosmology. In this model, rather than being an endpoint, a singularity acts as a bridge or transition point. The matter and energy compressed into the black hole are not destroyed, but instead bounce into a new phase of expansion, creating a new universe. This new universe would exist on the other side of the black hole, connected to our own by the singularity. From the perspective of the new universe, the singularity would appear as its Big Bang. The bounce cosmology model also provides a potential solution to the question of what happens to information that falls into a black hole. If black holes birth new universes, information might not be lost, but rather carried into the new universe, encoded in its initial conditions. If our universe originated from a black hole in another universe, it might inherit certain properties from its parent, such as fundamental constants or laws of physics. This could provide an explanation for why our universe seems fine-tuned for life. If universes are born from black holes, those with conditions favorable for black hole formation would be more likely to reproduce. This creates a kind of cosmic natural selection, where universes with black hole-friendly conditions proliferate. Some researchers have explored how this idea might be tested. One possibility involves studying the characteristics of black holes in our universe. If black holes are connected to new universes, they might exhibit subtle deviations from predictions made by classical physics. These deviations could manifest in their gravitational waves, Hawking radiation, or the dynamics of matter near the event horizon. Another avenue of exploration is the study of the early universe. If our universe originated from a black hole, the conditions of its birth might leave imprints on the cosmic microwave background radiation or the distribution of matter on large scales. These imprints could reveal clues about the nature of the black hole that created our universe, offering a glimpse into the parent universe from which we emerged. If universes can emerge from black holes, then creation is not a singular event but an ongoing process. This shifts the focus from a single origin point to a dynamic, interconnected multiverse, where black holes serve as gateways between realms. If our universe is the product of a black hole, then time as we know it began with the formation of that black hole. But what about the parent universe? Does it still exist, or has it been forever cut off from our own? While the cosmic seed hypothesis is rooted in established physics, it ventures into areas where our current theories are incomplete or untested. The nature of singularities, the behavior of space-time at quantum scales, and the interplay between general relativity and quantum mechanics are all areas of active research. As our understanding of these topics evolves, so too will our ability to evaluate the idea of black holes as cosmic seeds. Black holes as time machines, navigating causality. A time-like curve is essentially the path that an object or a person would take through spacetime, following the flow of time as we experience it. A closed time-like curve, however, loops back on itself. This means that an object following such a path could return to its own past, potentially witnessing or even altering events that have already occurred. Black holes, with their immense gravitational pull and the way they twist space-time, are one of the few environments where closed, time-like curves might exist. A rotating or Kerr black hole doesn't just pull matter inward, it also drags space-time around with it. This phenomenon, called frame dragging, creates a swirling effect in the surrounding space-time. If the black hole spins fast enough, it might theoretically create a region where closed time-like curves can form. This region, known as the ergosphere, lies just outside the event horizon. Inside the ergosphere, the effects of the black hole's rotation are so intense that nothing can remain stationary. It's here that some physicists speculate time loops could arise. The idea of using a black hole as a time machine isn't without its challenges. The tidal forces, which stretch and compress objects due to differences in gravitational pull, would likely tear apart anything attempting to navigate these regions. Even if a spacecraft could somehow withstand these forces, entering a closed time-like curve would require incredibly precise calculations and an understanding of physics that we don't yet possess. There's also the question of paradoxes. Time travel, especially to the past, is fraught with logical challenges, the most famous of these being the grandfather paradox, which asks, what happens if a time traveler goes back in time and prevents their own grandfather from meeting their grandmother? If the time traveler's grandfather never has children, then the time traveler could never exist. But if the time traveler doesn't exist, they couldn't have gone back in time to prevent their grandfather's meeting. This kind of circular logic creates a contradiction that's difficult to resolve. The principle of self-consistency, proposed by physicist Igor Novikov, suggests that any actions taken by a time traveler in the past must be consistent with the timeline they came from. In other words, events would unfold in such a way that paradoxes are avoided. For example, if a time traveler tries to prevent an event from happening, their actions might inadvertently cause the very event they were trying to stop. While this idea doesn't completely eliminate the strangeness of time travel, it offers a way to think about it without breaking the laws of physics. Some theories suggest that traveling back in time might create a new, branching timeline, a parallel universe where the traveler's actions can unfold without affecting the original timeline. In this scenario, the grandfather paradox is avoided because the time traveler's actions don't alter their own past, but instead create a new version of events. While this idea fits within some interpretations of quantum mechanics, it raises its own set of questions about the nature of reality and the connections between parallel universes. In our everyday experience, causes always precede effects. But in a universe where time loops are possible, this relationship could break down, leading to situations where effects influence their own causes. This challenges not only our understanding of time, but also the very structure of the universe. Some scientists remain skeptical about the idea of time travel through black holes, arguing that the conditions required to create closed time-like curves or stable wormholes might be impossible to achieve. Others point out that even if time travel is theoretically possible, it might be limited by fundamental laws we don't yet understand. For example, some theories of quantum gravity suggest that space-time might have a discrete structure at the smallest scales, which could prevent the formation of closed time-like curves or other time travel mechanisms. Are black holes the key to faster-than-light travel? The speed of light, approximately 300,000 kilometers per second, is a cornerstone of modern physics. Nothing with mass can accelerate to or exceed this speed, because the energy required would become infinite. However, relativity also describes how space-time itself can bend, stretch, and curve in the presence of mass and energy. This flexibility of space-time suggests that faster-than-light travel might not require breaking the speed of light itself, but instead manipulating the fabric of space-time to create shortcuts or warp bubbles. Unlike wormholes, which rely on creating a shortcut through space-time, a warp drive would manipulate space-time itself to achieve faster-than-light travel. The most famous example of this idea is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive works by contracting space-time in front of a spacecraft and expanding it behind, creating a bubble of flat space-time in which the spacecraft could travel. Theoretically, this bubble could move faster than light without the spacecraft inside breaking the speed of light relative to the bubble. The immense energy required to manipulate space-time might be harnessed from the rotational energy of a Kerr black hole. Some studies have explored the possibility of extracting energy from a black hole's ergosphere through a process known as the Penrose mechanism. This process involves sending matter into the ergosphere in such a way that part of it falls into the black hole, while the rest escapes with more energy than it had initially. If this energy could be harnessed and directed, it might provide the power needed to fuel a warp drive. The creation of a warp bubble, like the stabilization of a wormhole, would require exotic matter with negative energy. Additionally, the Alcubierre drive has been criticized for potential issues with causality and the creation of destructive radiation at the edges of the warp bubble. If wormholes or warp drives could be realized, they would revolutionize our ability to explore the cosmos. Interstellar distances, which currently take thousands or even millions of years to traverse using conventional technology, could be crossed in a fraction of the time. This would open up the possibility of visiting distant star systems, studying exoplanets up close, and even establishing colonies beyond our solar system. Can alien civilizations use black holes as energy sources? If advanced civilizations exist elsewhere in the universe, they would likely face immense energy demands as they develop technologies far beyond our own. Black holes, with their extreme energy-generating capabilities, might be seen as cosmic power plants by these advanced beings. Black holes are capable of generating incredible amounts of energy. This energy comes from the extreme conditions near their event horizons, where matter spirals inward at nearly the speed of light. The key to harnessing this energy lies in the accretion disk, a swirling mass of gas, dust, and other matter that forms around a black hole. As matter in the accretion disk is pulled closer to the black hole, it heats up to millions of degrees due to friction and gravitational forces, emitting vast amounts of electromagnetic radiation, particularly in the form of X-rays. For an advanced civilization, this radiation could represent a nearly limitless energy source. By constructing a structure around the black hole, the civilization could capture and convert this radiation into usable energy. The structure would need to be equipped to handle the intense X-rays and other high-energy emissions from the accretion disk. This would require materials capable of withstanding extreme radiation and heat, as well as technologies to efficiently convert this energy into a form that could be utilized. When matter falls into a black hole, a significant fraction of its mass is converted into energy. For a rotating black hole, this efficiency can reach up to 42%, far exceeding the energy conversion efficiency of nuclear fusion, which is the process powering stars. This high efficiency means that even a relatively small amount of matter could provide an advanced civilization with an extraordinary amount of energy. In addition to accretion disks, another potential energy source near black holes is Hawking radiation. While the amount of Hawking radiation emitted by large black holes is negligible, smaller black holes, known as micro-black holes, would emit much more radiation. An advanced civilization might create or capture micro-black holes and use their Hawking radiation as a controlled energy source. Physicists have explored methods such as the Penrose process, which involves harnessing the rotational energy of a spinning black hole. In this process, a particle is sent into the ergosphere, the region just outside the event horizon where space-time is dragged along by the black hole's rotation. The particle splits into two, with one part falling into the black hole and the other escaping with more energy than the original particle. This energy gain comes from the rotational energy of the black hole itself. For an alien civilization, the challenges of using black holes for energy would be immense, but not insurmountable, if they had reached a sufficiently advanced stage of technological development. These civilizations would need to master the construction of structures on an unprecedented scale. They might also need to address the safety concerns associated with operating near a black hole, as the intense radiation and gravitational forces could pose significant risks. If advanced civilizations are harvesting energy from black holes, they might leave detectable signatures that could be observed from Earth. For example, a structure around a black hole would partially block the radiation from the accretion disk, creating an unusual pattern of emissions that could be identified by astronomers. Similarly, the deliberate manipulation of matter near a black hole, such as the creation of micro-black holes or the use of the Penrose process, might produce observable effects. By studying the regions around black holes, particularly those with unusually low or altered emissions, researchers might find evidence of advanced civilizations at work. This approach expands the scope of the search beyond traditional methods, which often focus on detecting radio signals or other direct forms of communication. A civilization capable of harnessing the power of a black hole would need to have an extraordinary understanding of physics and engineering, as well as the ability to operate on cosmic scales. Such a civilization might be classified as a Type 2 or even Type 3 civilization on the Kardashev scale, a framework that categorizes civilizations based on their energy consumption. A Type 2 civilization harnesses the energy of an entire star, while a Type 3 civilization controls the energy of an entire galaxy. Using black holes for energy might represent a step toward or beyond these levels of development. The Dyson sphere. Black hole, a hypothetical power plant. Originally proposed by physicist Freeman Dyson in 1960, the Dyson sphere was imagined as a megastructure encircling a star to capture its energy output. This idea has since been expanded to include other energy sources, including black holes. Unlike stars, which emit energy in the form of visible light and other radiation from nuclear fusion, black holes generate power through mechanisms such as accretion disks, relativistic jets, and potentially Hawking radiation. These mechanisms provide unique opportunities for energy harvesting that surpass even the most efficient star-based systems. The accretion disk around a black hole emits radiation across a broad spectrum, from X-rays to gamma rays. The energy density of this radiation far exceeds that of sunlight emitted by a star, making it an incredibly concentrated source of power. A Dyson sphere constructed around a black hole would need to capture this intense radiation, converting it into usable energy while withstanding the extreme conditions present near the event horizon. The design of such a Dyson sphere would differ significantly from one built around a star. Traditional Dyson spheres, at least in theory, are imagined as solid shells, swarms of satellites, or rings surrounding a star at a safe distance to capture its energy. Around a black hole, however, the structure would need to account for the intense gravitational forces, high-energy radiation, and relativistic effects present in the vicinity. A solid shell would likely be impractical due to the gravitational instability of such a configuration. Instead, a swarm of satellites or a network of energy-collecting stations could be positioned in orbit around the black hole carefully balanced to avoid being pulled into the event horizon. One advantage of a Dyson sphere around a black hole is the compactness of the energy source. Stars are vast objects with relatively low energy density compared to black holes. A black hole with a powerful accretion disk could generate comparable or greater amounts of energy in a much smaller region of space. This compactness would allow for a Dyson sphere with a smaller radius, reducing the material and engineering requirements for construction. However, the proximity to the black hole would also mean dealing with stronger tidal forces, higher radiation levels, and the potential hazards of relativistic jets. A Dyson sphere designed to capture energy from relativistic jets would need to be positioned along the black hole's rotational axis, where the jets are most concentrated. This configuration would allow the structure to tap into the black hole's rotational energy, which is one of its most abundant and long-lasting resources. The extraction of rotational energy could be achieved through mechanisms such as magnetohydrodynamic interactions, which involve the coupling of magnetic fields and plasma flows. The structure would need to be composed of materials capable of withstanding extreme radiation, heat, and gravitational forces. It would also need to include advanced energy conversion systems to efficiently capture and store the radiation emitted by the black hole. The logistics of constructing such a structure, including the transport of materials and the assembly of components in the hostile environment near a black hole, would require a level of coordination and innovation that is difficult to imagine. For an advanced civilization, the benefits of such a project could outweigh the challenges. This energy could be used to power interstellar travel, large-scale computational systems, or other advanced technologies. The compactness and efficiency of the system would also make it an attractive option for civilizations seeking to maximize their energy output while minimizing their spatial footprint. Electroweak black holes. What if the weak force went rogue? Electroweak black holes represent a fascinating idea that connects the physics of black holes to the fundamental forces governing particles in the universe. To understand this concept, we must look back to the earliest moments of the cosmos, a time when the universe was unimaginably hot and dense. During this period, the forces of nature were unified in ways that are not seen today. As the universe expanded and cooled, these forces began to separate, undergoing transitions that defined the structure of the universe as we know it. One of these key transitions is known as the electroweak phase transition. The electroweak force, as its name suggests, is a combination of two of the fundamental forces, the electromagnetic force and the weak nuclear force. At extremely high temperatures, such as those present in the first fractions of a second after the Big Bang, these two forces were indistinguishable, acting as a single, unified force. However, as the universe cooled, this symmetry broke, and the electromagnetic and weak forces separated into the distinct entities we observe today. This event is called the electroweak phase transition. The electroweak phase transition wasn't necessarily smooth or uniform across space. Just as water can freeze into ice with cracks and bubbles forming during the process, the cooling of the universe might have created regions of instability and intense energy. These regions could have collapsed under their own gravity, leading to the formation of electroweak black holes. Unlike the black holes we observe in space today, which are formed from the collapse of massive stars or the merging of stellar remnants, these would have formed directly from the energy fluctuations and instabilities during the phase transition. Electroweak black holes would be incredibly small compared to stellar black holes, with sizes determined by the energy scales of the electroweak force. This means they would be microscopic, likely smaller than an atom. Despite their small size, their formation would still require an immense concentration of energy, enough to warp spacetime and create an event horizon. These tiny black holes would have existed in a universe vastly different from the one we know today, one filled with a hot, dense soup of particles moving at nearly the speed of light. They could have played a role in shaping the distribution of matter and energy as the cosmos expanded. If they were created in significant numbers, their gravitational influence could have acted as seeds for the large-scale structures we see in the universe, such as galaxies and galaxy clusters. Additionally, as these black holes evaporated through Hawking radiation, they would have released particles and energy back into the universe, potentially contributing to the formation of the first atoms and elements. The energy scales associated with the electroweak force are well within the range of energies that particle physicists study in experiments today. This raises the question of whether similar conditions could be recreated in laboratories using high-energy particle accelerators. If it were possible to generate the extreme energy densities required, it might be feasible to produce microscopic black holes in controlled settings, providing direct evidence for the processes that occurred during the electroweak phase transition. Dark matter, which makes up a significant portion of the universe's mass, remains one of the biggest mysteries in modern astrophysics. Some researchers have speculated that primordial black holes, including those formed during the electroweak phase transition, could account for at least part of the dark matter. If electroweak black holes existed and survived to the present day, they might be detectable through their gravitational effects on surrounding matter or their emissions as they slowly evaporate. Another area of interest is the role of electroweak black holes in baryogenesis, the process that created the imbalance between matter and antimatter in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts, but today we observe a cosmos dominated by matter. The mechanisms that led to this asymmetry are not fully understood, but the intense energy environments around electroweak black holes could have provided conditions favorable for such processes. The interactions of particles near these black holes might have amplified tiny imbalances, ultimately shaping the matter-dominated universe we inhabit. Quark black holes, when fundamental particles collapse. Quarks are the fundamental particles that combine to form protons, neutrons, and other hadrons. These particles are incredibly small, but their interactions give rise to the complex structures that make up all matter. The notion of quark black holes suggests that under extreme conditions, these particles could collapse into a singularity, forming black holes. Quarks are unique among particles because they experience a force known as the strong nuclear force, which is responsible for binding them together inside protons and neutrons. This force becomes stronger as quarks are pulled apart, effectively confining them to their bound states under normal conditions. However, at extremely high energies and densities, such as those found in the cores of neutron stars or during the earliest moments of the universe, the rules governing quarks may change. In these environments, quarks might break free from their confined states, creating a form of matter known as quark-gluon plasma. Quark-gluon plasma is a state of matter where quarks and gluons, the particles that mediate the strong force, move freely. This plasma is thought to have existed for only a fraction of a second after the Big Bang, before cooling into the matter we see today. However, some theories suggest that in regions of extreme density, quark matter could collapse further, leading to the formation of a quark black hole. Instead of being made from the remnants of ordinary matter, they would originate directly from the collapse of fundamental particles. Because quarks are much smaller than atoms, a black hole formed from collapsing quarks would also be extremely small. Despite their size, these black holes would have immense densities, far surpassing anything found in ordinary stellar black holes. The immense gravitational pull of a quark black hole would compress space-time around it to an extreme degree. Their event horizons would be tiny. This means that their interactions with the surrounding environment would differ significantly from those of stellar black holes. The process of Hawking radiation might occur at an accelerated rate for quark black holes. This could cause them to evaporate more quickly, releasing their energy back into the universe. Theoretical physicists have speculated about the conditions under which quark black holes might form. One possibility is that they could arise in the dense cores of neutron stars, where matter is compressed to incredible densities. Neutron stars are already among the densest objects in the universe, but some theories suggest that if their cores reach a critical density, the neutrons could break down into their constituent quarks. If this quark matter becomes unstable, it could collapse into a black hole. Such an event would create a quark black hole within the neutron star, potentially leading to its complete collapse. Do the laws of physics allow for the formation of such objects? If they exist, what role do they play in the universe's evolution? Can we find evidence of their existence through observations or experiments? These questions drive ongoing research and highlight the importance of exploring the unknown. Magnetically charged black holes, theoretical monsters of magnetism. Black holes are known for their gravitational pull. But what if a black hole could possess a magnetic charge in addition to its mass and spin? Magnetically charged black holes, if they exist, would combine the intense gravity of black holes with powerful magnetic forces, creating some of the most extreme environments in the universe. The possibility of a magnetically charged black hole arises from the study of certain solutions to Einstein's equations of general relativity, particularly when combined with theories that include magnetic monopoles. A magnetic monopole is a hypothetical particle that carries a single magnetic charge, either north or south, unlike the magnetic dipoles we see in everyday magnets. While no magnetic monopoles have been observed in nature, they are predicted by some extensions of the standard model of particle physics, as well as grand unified theories that attempt to explain the forces of nature within a single framework. In the context of black holes, the idea of a magnetic charge comes from the analogy with electrically charged black holes. These are solutions to Einstein's equations where a black hole can carry an electric charge, creating what is known as a Reissner-Nordström black hole. Similarly, if magnetic monopoles exist, a black hole could, in theory, acquire a magnetic charge by capturing these monopoles. The result would be a magnetically charged black hole, sometimes referred to as a magnetic black hole or a dionic black hole if it carries both electric and magnetic charges. The presence of a magnetic charge would significantly alter the behavior of a black hole and its interaction with the surrounding environment. A magnetically charged black hole would generate an intense magnetic field that extends beyond its event horizon. This magnetic field would interact with any charged particles in the vicinity, creating powerful electromagnetic effects. Particles with an electric charge, such as electrons or protons, would spiral around the magnetic field lines, producing high-energy radiation in the process. This could result in unique observational signatures, such as specific patterns of electromagnetic waves or bursts of radiation. The interaction between the magnetic field and the accretion disk of a black hole could also be dramatically different. In the case of a magnetically charged black hole, the magnetic field could influence the motion of charged particles in the disk, altering its structure and dynamics. The field might even drive powerful jets of plasma away from the black hole, similar to those observed in some active galactic nuclei, but with distinct properties due to the magnetic charge. Magnetic fields are a common feature of the cosmos, observed in everything from planets and stars to galaxies and clusters of galaxies. However, the origin of these fields remains a mystery. Some theories suggest that magnetically charged black holes could act as seeds for the generation of cosmic magnetic fields. As these black holes interact with their surroundings, they could amplify and distribute magnetic fields across vast regions of space. How would the presence of a magnetic charge affect the black hole's event horizon or its singularity? Would the magnetic charge influence the black hole's stability or its ability to evaporate through Hawking radiation? These questions are difficult to answer without a unified theory of quantum gravity. In classical physics, gravity and electromagnetism are distinct forces with very different behaviors. Gravity is always attractive and acts on mass, while electromagnetism can be both attractive and repulsive, depending on the charges involved. In a magnetically charged black hole, These forces would coexist in a single object, creating a highly complex and dynamic environment. Another fascinating aspect of magnetically charged black holes is their potential connection to high-energy astrophysical phenomena. Some gamma-ray bursts, which are among the most energetic events in the universe, could be linked to the formation or interaction of magnetically charged black holes. Similarly, these black holes might play a role in the acceleration of cosmic rays, the high-energy particles that travel through space and occasionally strike Earth's atmosphere. The magnetic fields of these black holes could serve as natural particle accelerators, boosting particles to extreme energies. Despite their theoretical appeal, the existence of magnetically charged black holes remains speculative. The first challenge is the lack of direct evidence for magnetic monopoles, which are essential for a black hole to acquire a magnetic charge. If monopoles do exist, they are likely extremely rare or difficult to detect, which limits the opportunities for magnetically charged black holes to form. Additionally, even if such black holes do exist, their unique properties might make them difficult to observe with current technology. Advances in observational astronomy, such as the development of next-generation telescopes and detectors, could provide new ways to identify these objects. For example, astronomers might look for unusual patterns of radiation or magnetic fields that cannot be explained by ordinary black holes. Theoretical research also continues to explore the implications of magnetically charged black holes. By simulating their behavior and interactions, scientists can develop models that predict how these objects might appear in observations. These models can then be tested against real data, helping to refine our understanding of these exotic entities. Dark matter. Black holes. Could they explain the universe's missing mass? Dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. Scientists estimate that dark matter accounts for about 27% of the universe's total mass energy content, yet its nature remains elusive. In the quest to uncover its secrets, some researchers have proposed a fascinating connection between dark matter and black holes. Could black holes be composed of or closely interact with dark matter, helping to explain its mysterious properties? While its exact composition is unknown, scientists hypothesize that dark matter could be made up of exotic particles that interact weakly with ordinary matter and electromagnetic forces. These hypothetical particles, such as WIMPs, aka weakly interacting massive particles or axions, would exert gravitational effects but remain otherwise undetectable. If such particles exist, they could interact with black holes in unique and potentially revealing ways. Because dark matter responds to gravity, it could be drawn toward a black hole's immense gravitational pull. Unlike ordinary matter, which forms an accretion disk and heats up as it spirals inward, dark matter would behave differently. Without significant electromagnetic interactions, dark matter particles would not collide and lose energy in the same way. Instead, they might form a dense halo or spike around the black hole. These dark matter structures could alter the black hole's gravitational signature, making it distinct from black holes surrounded only by ordinary matter. Detecting these differences could provide crucial evidence for the presence of dark matter near black holes. The motion of stars and gas around a black hole could reveal subtle deviations caused by the additional gravitational influence of dark matter. Similarly, the way gravitational waves are emitted during black hole mergers might carry hints of dark matter's presence. By studying these signals, scientists could gain insights into the properties and distribution of dark matter. Another idea is that some black holes might be composed entirely of dark matter. These hypothetical objects, often called dark matter black holes, would form if regions of dark matter became so dense that they collapsed under their own gravity. Unlike traditional black holes, which form from the collapse of massive stars, dark matter black holes would not emit light or radiation during their formation. This makes them even harder to detect, as they would blend seamlessly into the dark cosmic background. If dark matter black holes exist, they could explain some of the universe's missing mass. Observations of galaxies and galaxy clusters reveal that there is far more mass present than can be accounted for by visible matter alone. This unseen mass, attributed to dark matter, could include a population of dark matter black holes scattered throughout the universe. If dark matter interacts with black holes, it could influence the rate of Hawking radiation or leave detectable imprints on the emitted particles. Studying these effects could offer indirect evidence of dark matter's properties and behavior. Some theories propose that the interaction between dark matter and black holes could produce unique signals, such as high-energy particles or gamma rays. For instance, if dark matter particles annihilate each other when they collide, the dense environment near a black hole could act as a catalyst for such interactions, generating detectable radiation. Observatories like the Fermi Gamma Ray Space Telescope and other high-energy detectors are actively searching for these signals. Despite the excitement surrounding the idea of dark matter black holes, there are significant challenges. For one, distinguishing the effects of dark matter from other astrophysical phenomena is extremely difficult. The gravitational effects attributed to dark matter could also be explained by alternative theories of gravity, such as modified Newtonian dynamics, or MUND, as well as other extensions of general relativity. These competing ideas complicate the interpretation of observational data. Additionally, the rarity and invisibility of dark matter make it challenging to confirm its direct interaction with black holes. Even if dark matter clusters around black holes or forms them, the signals might be too faint or subtle to detect with current technology. Advancements in observational techniques will be crucial in addressing these challenges. What if a black hole appeared in our solar system? If a black hole were to appear in our solar system, the consequences would be profound and immediate. The sheer gravity of such an event, both figuratively and literally, would reshape the delicate balance that has governed our solar system for billions of years. Black holes, with their immense gravitational pull, warp space and time around them. Their introduction into a stable system like ours would disrupt planetary orbits, gravitational dynamics, and potentially even the Sun's ability to sustain its own processes. Each planet in the solar system follows a stable path around the Sun, a balance maintained by the interplay between gravitational forces and the planet's momentum. A black hole, depending on its size and mass, would drastically alter this balance. If the black hole were relatively small but massive, such as a stellar mass black hole, it could start pulling objects out of their orbits, dragging them closer to itself, or flinging them into deep space. If it entered the solar system far from the Sun, in the outer regions where the Kuiper Belt and Oort cloud reside, the first noticeable changes might involve distant objects like comets and dwarf planets. The black hole's gravity could start pulling these icy bodies inward, sending a barrage of comets hurtling toward the inner solar system. These incoming objects could collide with planets, moons, or even the Sun, creating spectacular but catastrophic impacts. Closer to the Sun, the disruption would be even more dramatic. The planet's orbits could be stretched into ellipses or destabilized entirely. For example, if the black hole passed near Jupiter, it could alter the gas giant's orbit significantly. Jupiter's massive gravity helps stabilize the orbits of many other objects in the solar system, including asteroids in the asteroid belt. Any change in Jupiter's position could trigger a cascade of effects, causing chaos among smaller celestial bodies. Earth, being in the habitable zone of the solar system, relies on its stable orbit to maintain the conditions necessary for life. If a black hole disrupted Earth's orbit, even slightly, the consequences could be devastating. A shift closer to the Sun would result in scorching temperatures, boiling away oceans, and rendering the planet uninhabitable. A shift farther from the Sun would plunge Earth into a deep freeze, freezing the surface and extinguishing most forms of life. even if the orbit remained largely intact. The tidal forces from the black hole could cause massive geological upheavals, triggering earthquakes, volcanic eruptions, and tsunamis. The Sun itself might not escape unscathed. While a black hole smaller than the Sun wouldn't directly consume it, the gravitational interplay between the two could affect the Sun's internal dynamics. The Sun relies on a delicate balance between gravitational pressure and nuclear fusion to maintain its stability. A close encounter with a black hole could disturb this equilibrium, potentially accelerating or disrupting the fusion process. This could lead to changes in the Sun's energy output, affecting the entire solar system. If the black hole were to pass directly through the Sun, the results would be even more catastrophic. The intense gravitational forces could rip through the Sun's core, causing a temporary collapse or triggering a massive release of energy. Such an event could produce a burst of radiation that would irradiate the inner planets, including Earth. The Sun might recover over time, but the damage to the solar system would be irreversible. One of the most terrifying aspects of a black hole entering the solar system is the potential for spaghettification, the process where objects are stretched and torn apart by intense gravitational forces. If the black hole came close enough to Earth, the tidal forces could stretch the planet into an elongated shape, pulling it apart piece by piece. The same fate would await any other celestial body that ventured too close, including the Moon, which could be shredded into a debris field. The black hole's accretion disk, if it had one, would add another layer of danger. The radiation, primarily in the form of X-rays and gamma rays, could bathe the solar system in deadly energy. The protective layers of Earth's atmosphere and magnetic field might shield some of this radiation, but the levels could still be enough to cause widespread destruction to life and technological systems. If the black hole were small enough, such as a primordial black hole, its effects might be less catastrophic but still significant. A primordial black hole passing through the solar system could carve through planets and moons without consuming them entirely, leaving behind trails of destruction. Such a black hole might even pass through Earth itself, creating a narrow but deep tunnel through the planet as it moved. The energy released during this process could cause localized destruction, such as massive earthquakes and volcanic eruptions. Humanity's ability to respond to such an event would depend on the speed at which the black hole entered the solar system and how quickly its effects became apparent. If the black hole appeared suddenly, with no warning, there would be little time to prepare. However, if it were detected while still far away, scientists might have centuries or even millennia to study its trajectory and develop strategies for mitigating its impact. Potential responses could include attempting to alter the black hole's path using gravitational interactions or deploying advanced technologies to shield Earth from its effects. The presence of a black hole in the solar system would also provide an unprecedented scientific opportunity. Despite the dangers, astronomers and physicists would likely attempt to study the black hole up close, using it to test theories of gravity, quantum mechanics, and general relativity. Observations of the black hole's interactions with the Sun and planets could yield new insights into the behavior of these mysterious objects. Is reality itself a simulation run by a black hole? In the context of simulation theory, some researchers have speculated that black holes could act as computational hubs. The basic premise is that the information absorbed by a black hole, from stars, planets, and even light, isn't destroyed as it disappears beyond the event horizon. Instead, this information could be processed or stored in a way that is beyond our comprehension. This idea aligns with the principle of information conservation, which suggests that information in the universe cannot be lost, even in the presence of a black hole. Now consider the idea that black holes, as massive processors of information, could serve as nodes in a vast computational network. Each black hole might function like a supercomputer, taking in data from its surroundings, performing complex calculations, and contributing to the overall structure of a simulated universe. The connections between black holes, perhaps through mechanisms like quantum entanglement or wormholes, could allow for the transfer and synchronization of information across the cosmos. This interconnected network could, in theory, sustain the intricate patterns and rules that govern our reality. Entropy is a fundamental concept in understanding the flow of energy and information in the universe. Black holes are often described as the ultimate entropy sinks, absorbing vast amounts of matter and energy. If they are indeed processing this information, they could be performing calculations that contribute to the evolution of the universe. These calculations might determine the behavior of particles, the formation of galaxies, or even the emergence of conscious beings like ourselves. If our reality is a simulation, then our thoughts, actions, and experiences might be the result of computations performed by black holes or the larger network they form. Are we simply complex patterns of data being processed within an unfathomable cosmic machine? Or is there something more to our existence that transcends the boundaries of a simulated reality? Critics of this hypothesis often point out that while the mathematical and theoretical frameworks supporting ideas like the holographic principle are robust, they do not prove that black holes are computational entities or that our universe is a simulation. Moreover, the concept of a simulated reality itself is difficult to test scientifically. If we are part of a simulation, how would we ever detect the underlying mechanisms without stepping outside the system? These challenges highlight the speculative nature of the hypothesis, even as it sparks profound philosophical and scientific discussions. If black holes are computational nodes, could an advanced species have designed them as part of a larger simulation? This notion aligns with the idea that a sufficiently advanced civilization might create simulated universes for research, entertainment, or other purposes. The black holes in our universe could then be the tools or infrastructure used to sustain such simulations. This perspective invites us to consider the possibility that our reality is not only a simulation, but also the product of intentional design. Entangled horizons. Are all black holes quantumly connected? Entanglement is a well-known phenomenon in quantum physics, where two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are. Extending this idea to black holes raises intriguing possibilities, suggesting that these cosmic objects could be part of a larger, interconnected web spanning vast regions of space-time. At the heart of this concept is the realization that black holes are not isolated entities. Their horizons may act as surfaces where quantum information is stored and processed. In quantum theory, entanglement doesn't just occur between particles, it can also occur between larger systems, including black holes. This idea has gained traction in theoretical physics, particularly as scientists try to reconcile the principles of quantum mechanics with the curvature of space-time described by general relativity. One of the key proposals in this area is the ER equals sign EPR conjecture, introduced by physicists Juan Maldacena and Leonard Susskind. This hypothesis suggests that Einstein-Rosen bridges are equivalent to entangled particle pairs, described by Einstein-Podolsky-Rosen correlations in quantum mechanics. Essentially, the conjecture posits that two black holes connected by a wormhole are fundamentally entangled. If true, this would mean that black holes are not just massive gravitational objects, but also nodes in a quantum network. If black hole horizons are entangled, then information about one black hole might be accessible through its entangled partner, regardless of the distance between them. This could offer a potential resolution to the black hole information paradox, with entanglement serving as a mechanism for information to be shared or transferred across space-time, preserving it in ways that defy classical understanding. To visualize how this might work, imagine two black holes that formed from a single event, such as the collapse of a massive star. According to quantum mechanics, the particles that make up the black holes could retain their entangled states, linking the two horizons. Even as the black holes drift apart due to cosmic expansion, their entangled connection could persist, acting as a quantum bridge. Any changes to one black hole's horizon could instantaneously affect the other, regardless of the intervening distance. If black holes are entangled, they might influence the behavior of space-time on a larger scale. For instance, the entanglement of horizons could create subtle correlations in the cosmic microwave background, or CMB. Observing these correlations could provide indirect evidence for the entanglement of black holes and offer new insights into the nature of space-time itself. One of the challenges in studying entangled horizons is the difficulty of observing them directly. Black holes are inherently elusive. However, indirect evidence might come from the study of gravitational waves, ripples in space-time produced by the merging of massive objects like black holes. If the horizons of merging black holes are entangled, their interaction could leave subtle imprints on the gravitational waves they produce. Advanced detectors, such as LIGO and Virgo, might one day be able to identify these imprints, offering a glimpse into the quantum nature of black holes. In classical physics, nothing can travel faster than the speed of light. Yet, quantum entanglement appears to operate instantaneously, defying this limitation. If black holes are entangled, does this mean that information can be shared across vast distances without regard for the speed of light? While this might seem to violate relativity, some physicists argue that entanglement doesn't involve the transfer of information in the traditional sense, preserving the integrity of Einstein's theories. There are also speculative ideas about how entangled black holes could be used for advanced technologies. If the entanglement of horizons allows for the transfer of information, it might be possible to harness this phenomenon for communication across cosmic distances. Such a system would operate on principles far beyond our current understanding, potentially enabling civilizations to share information across galaxies without the need for physical travel. If black holes are interconnected through quantum entanglement, they might influence the distribution of matter and energy on a cosmic scale. This could help explain the large-scale structure of the universe, including the formation of galaxies, clusters, and voids. By studying the potential connections between black holes, scientists might uncover new principles governing the universe's growth and organization. The idea that all black holes might be quantumly connected suggests that the universe is far more interconnected than we currently understand, with black holes serving as gateways to a deeper reality. While many questions remain unanswered, the study of entangled horizons offers a unique opportunity to explore the mysteries of space-time, quantum mechanics, and the fundamental nature of the cosmos. As theoretical models evolve and observational techniques improve, we just might one day unlock the secrets of these enigmatic connections, reshaping our understanding of the universe. And with that thought, this video must come to an end. What other weird and wonderful ideas would you like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.